Okay, we'll actually start with the world of multitasking. So systems run many processes concurrently, right? What does that mean? Well, on a single core system, that means the processes take turns, time sharing. We move from process to process to process very quickly. Why do we do that? It gives us two things that so-called batch systems don't give us, right? One model is we feed one process, then we feed another process, then we feed another process, then we feed another process, one at a time, okay? We just use a queue, first in, first out. Another model is this time sharing thing, right? The time sharing thing gives us two things, the other thing doesn't. Right? One is the ability to be interactive, right? If I'm trying to interact with a user, and the user wants to use the word processor, to use instant messaging, and to use, the internet, these are not things that can be batch scheduled. We can't batch run your instant messaging, right, 15 minutes from now, right? That's interactive. You need to type something and have it sent so somebody else can type something and have it sent, right? You can't use an art program, right, as a batch program, right? You can't send it all your mouse movements at once and then come back later and see your rendering, right? It allows us to have systems that are interactive. It also allows us to make more efficient use of resources, okay? Because if we have multiple processes on a system, we have this traditional I/O CPU burst cycle where things read in input, process that input, and then write out the results, right? If we have multiple processes, we can have one that's in the input phase, let's say from disk, another that's in the thinking phase. Put your cell phone away. Away. I'm now on cell phone patrol. Listen, you've got the eyes in the sky back here. Can you do me a favor and just occasionally pan? Check for those cell phones, sort of like Vegas, flag violators, or just zoom in, and we'll post the conversations later. Okay. How's that? Okay. So, sorry. So, by having multiple processes, we can have them using different resources. Maybe we can have one reading from the network, another reading from disk, another processing some data. Right? And now we can get all of these resources in the game at the same time. Does that make sense? That makes things run much faster because everything is in use. Okay. So it gives us interaction, okay, and it gives us better resource utilization. Of course, the problem is there's this common resource all processes need, and that's memory, right? And there's a very finite amount of memory. And we've talked about the memory hierarchy, right? When you run out of RAM, you start to use disk. And so if you have too many processes, okay, you run into this situation called thrashing. I love that word, thrashing. Called thrashing. What happens is, you go to bring a process in, right? You go to run part of the process, and it says, shoot, right? There's not enough memory here, right? I need more RAM, right? So some other process gets written to disk. Or part of it gets written to disk. Now we've freed up some memory, right? So this process starts to run and then blocks because it needs memory. Some other process gets written part of it out to disk. Okay? Now, some other process starts to run and needs memory, right? And grabs the memory that was available. It now needs to read something in from disk. And basically what happens is we have so many processes that we can't keep any of them in memory. And we spend our entire time reading things from memory and writing them to disk. Because every time I go to run, the memory that was freed to me is gone by the time I get to use it. And now the system is reading and writing constantly, but never has the stuff it needs in memory for a process. And so it can't get any work done. That's when your level of multi-programming or multitasking is too high. Too many processes for the size of the core. It's worse than having too many processes for CPU, because then you just queue up for the CPU and you eventually get there, right? The problem with memory is that you can actually get into this situation where you're not making progress because you're juggling the same memory and it's never available when it's needed. It's called thrashing. Okay. So to execute a program, we need the memory image, the registers, and the program counter. We regularly switch from one process to another. And the cool thing is that if we do this fast enough, it actually appears to you and 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 to all the users of the system like they own the whole system. We each SSH into Unix 4.Andrew or whatever, and we don't worry about who else is on that system. There are enough resources for us to all share. We all take turns, but we don't even notice it so fast. We don't know that between us typing A and B and C and D, 6 other users may have done the same thing. It just takes turns quickly enough. Okay. We talked about the programmer's view of multitasking, right? Fork to create a process, exit to exit a process, wait and wait PID to reap a process, exec VE to replace a process image with one from disk. The programmer's challenge is to understand what's going on in this world when we have this concurrency, which is really hard on the human brain because we're used to thinking of A, then B, then C, then D. We're not used to thinking of what happens at once. Right? Think about it. If you go to tell somebody a story, and the story has 4 different characters in it, what do? You tell the story about what's happening with one character, then what's happening to another character, then what's happening to another character. You tell it from different perspectives. And meanwhile, blah. We have no way of actually, as humans, describing things as concurrent. The best we can do is describe something, and describe something else, and describe something else, and describe something else. Yes?
When you have stuff like program priority, or what's called niceness in Linux, is it, for high priority, is it the OS gives them bigger time slices, or is it the program is able to request resources with just time priority?
So the question is, how does priority work when it comes to scheduling? That's a little bit of a nuanced question, but you asked, how does it work, and does it give them bigger time slices? So let me answer the second question first. It does not give them bigger time slices, because the time slices are set by hardware. There's a timer that's set. It's actually a hardware timer, and it generates an interrupt every interval. So at boot time, you might set it and say, give me an interrupt every 10 milliseconds, or give me an interrupt every 100 milliseconds. And that's what defines the time quantum. Okay? And then what happens is, when that interrupt handler goes off, that's the operating system scheduler. Now, the operating system scheduler looks at the processes that it has available to run that are runnable, okay, and it asks, which one should I run right now? And in general, it will run the highest priority process it needs to run. Does that make sense? Which may be the one it's running, or it may be some other one. But in general, how it determines the highest priority process is based upon some a priority, based upon this niceness value that the user can set, and based upon how much this process has run recently. And so there's sort of a static value and a penalty value. And so when you have most processes in the system have about the same priority, and so it turns out the penalty for running recently controls most of the scheduling on most schedulers. Having said that, if you're doing real-time scheduling or things like that, then the priority becomes much stricter. Those classes don't move with penalties, if that makes sense. Okay. So at any rate, so we've seen this. Our challenge is to wrap our brains around this because it's really not natural for us. Okay? Unix process hierarchy. Don't make too much of this slide. What this slide tells us is that we bootstrap the system. And as part of the bootstrap, after we do the bulk of it, this process called init runs. And init has process ID 1. And init starts up a whole bunch of things as prescribed by some configuration files. Okay? And ultimately, the login shell that you have is going to be a child of init. Okay? Init is what is going to fork to create your login shell. And then from your login shell, you can create more processes. You can fork. And that's how when you do ls or rm or cp or vi, that's how your login shell does this. It calls fork. If it's a foreground process, it calls fork and wait. If it's a background process, it calls fork and doesn't call wait. And then your process is free to create more of its own processes. You guys are going to write a simple shell. Your simple shell is going to begin sort of like this, with a basic work loop. The work loop is going to prompt the user, read the user's input, and then act upon it. And then loop back and do it again. Right? What's the Unix shell? If you haven't played with the Unix shell, take the opportunity. Sit down, type a little bit. Right? Back in the day, right, everybody played with shells. Because, you had a Commodore 64 or an Apple II or an IBM PC. You ran DOS or something like that. Even in the early Windows days, you had to pop up a shell to get some things done. But these days, the reality is most of us use our computer every day without ever popping up a shell. We just use the GUI. So it's not strange that you guys might be actually unfamiliar with this. So if you are, sit down at a Unix machine, pop up a shell, and actually do some of the stuff that we've talked about. And we talked about in the Unix little help tutorial earlier on. I know you can find ways around it, right? Uploading and downloading your things with GUIs and whatnot. But take a few minutes and use the shell. Why? You're going to write one. It's a lot easier to write one if you know what you're writing. Screen full of code. Okay. In this chunk of code over here, we had this function called eval. And I said eval is basically where we do whatever the user asked us to do when they fed input to the command line, right? When we prompted them and they gave us stuff. And here's the function that does it. So what does it do? It parses it, and then it figures out if it's a built-in command, something like jobs, to show the shell's current jobs list. Okay? And if it's not a built-in command, then it's going to do a fork to create a new process, and do an exec to turn that new process into whatever the user asked for. ls, vi, cp, rm, whatever. And then if it's not a background job, it's going to wait for it. If it is a background job, it's not going to wait. In either case, it's going to loop back around, right? Because this function is going to end, and it's going to do it again. So we prompt the user, get the input from the user, act upon the user's input. We wait here if it's a foreground job. We don't wait here if it's a background job. And in either case, when the time comes, we loop back and do it again. Okay. What's a background job? Well, generally, we run things one at a time, like vi, and then we're looking at vi, right? ls, it runs. But sometimes we want to run a job in the background. We want to let something process. We want to search a directory for files that begin with a particular name, or files that contain a particular name, and write the results somewhere. And it's going to be grepping a big tree, right? grep minus r, tilde gkesden, grep minus r, I don't know, midterm grades, tilde gkesden. Okay? That's going to go through my whole directory looking for files that contain midterm grades. That might take a while. I've been collecting stuff in that directory for 16 years. Okay? So what might you do? Greater than, redirect it to a file, results.txt. So now my results are all getting written to this file, but I'm still waiting for them. So what might I do? grep minus r, midterm underscore scores, space tilde gkesden, greater than, results.txt, ampersand, right? Ampersand. This funky thing that says do it in the background. And now I can go about my merry business. Meanwhile, this thing's running in the background, searching for the files I want. Does that make sense? I saw a question over here. Nope? Okay. So here's an example, right? I'm sleeping for 2 hours and then removing a file called junk. Semicolon just means do this, then do this. Okay? Here's a case where I created a subshell. That's what parentheses do. It causes my shell to fork another shell. And this other shell, instead of running in the foreground, is going to run in the background, ampersand. And in this other shell, I'm going to wait for 2 hours and then remove this file called junk. What's this simulating? This is simulating running some long-running process like my grep, and then deleting a temp file when it's done. Okay? So background jobs let me move on while that job moves forward. Eventually that background job will end, right? Unless we wait for it, it becomes a zombie. How we wait for it turns out to be an interesting question. Okay? And this involves a mechanism called signals. And we're going to talk about that in a minute. But I'm going to give you a little bit of a preview. Signals are basically like interrupts, but they're a software version of interrupts. They're used to poke a process instead of poke the processor. So when a child dies, the operating system says, okay, this process just died. I need to notify its parent. So it signals the parent by sending the parent a signal called sigchild. S-I-D-C-H-L-D. Sigchild. Dear parent, your child just changed state, meaning it became suspended or died. Much like we have interrupt handlers for hardware interrupts, we have signal handlers for these software interrupts. So when I install a new, if I want to pay attention to a signal, I install a handler for that signal. So now the shell has installed a handler for SIGCHILD. When a child dies, the SIG handler fires off, just like an interrupt handler would fire off. It handles that signal, meaning it uses wait to reap the child. Now the child is reaped. The signal handler returns, and the process goes back to doing what it was doing before. It's asynchronous, just like a hardware interrupt is. Okay. So you want to make sure you reap your zombies, because zombies take resources. They're still hanging around, right? And it's just a little bit of a resource, but if you get enough of them, you run your system out of memory. Okay. There's a limit as to how many processes you can have. Here you can see on this system it's set to 202,752. And so when you exhaust that, you can't fork new processes. Fork returns a -1. So let's talk about signals. A signal is a small message that notifies a process that an event of some type has occurred in the system. In other words, it's a poke. It's a software interrupt. It's like exceptions and interrupts. It's sent from the kernel to the process. Okay. It can be sent because the kernel wants to poke the process, or it can be sent at the request of one process. For example, if you hit Control-C in your shell, what happens? It cancels what? The current process. So if I have a foreground process running in my shell and I hit Control-C, it cancels the current process. Right? In that case, that signal is being sent at the request of another process to the dying process. We'll talk about that. Signals basically are simple integers. We give them names, but they're just integers. These integers are the index, right, into an array of signal handlers, akin to the array of interrupts. A kernel sends a signal to a destination process by updating some state in the context of the destination process. The kernel sends a signal for one of the following reasons. The kernel's detected a system event, or another process has invoked kill. Okay, the way one process sends a signal to another process, bizarrely, is through a call named kill. Kill means send signal. Okay? Why, historically, the signal you would send would be die? Now it's more general than that. So there are 3 data structures associated with signal handling. Okay? These are per process data structures. We'll see them in a minute, but I'm going to give you the overview now. One process is an array of signal handlers. It's just like the interrupt array. Okay? It's an array of function pointers with an integer index. Right? Like any other array. The signal number is the index into this array. This signal ID is the index into the array of signal handlers. Does that make sense? So if a process gets sent signal number 17, it's going to execute the 17th signal handler. Does that make sense? Now, it needs to know when to do that. So in addition to the array of signal handlers, there is an array, okay, called the pending signal mask. It's 1 bit per signal, basically. Okay? And if the kernel sends you a signal, all it does is flip your bit to on. Does that make sense? So if your process accesses memory it shouldn't access, because you have a bad pointer, the kernel will send you a segment violation. It does this by going into your process control block, your task struct, the kernel's data structure representing your process, and flipping that 1 bit on, saying that signal is pending. That's it. That's what it means to deliver a signal. It means to flip the pending bit on. What happens if the pending bit was on before the signal was delivered? It stays on. Does that make sense? There's no queue, there's no count, it's just a bit. So if 2 signals are sent before any of them are handled, the bit is still set. That means that when we interpret that bit, we interpret to be 1 or more signals have been sent. If the bit is sent for, SIGCHILD, we interpret that to be 1 or more SIGCHILDs have occurred. We can't tell if it's 1 or if it's 2 or if it's 3. We know it's not 0. Does that make sense? So, if the kernel sends you a signal, whether it's because of some event like you access bad memory, or it's because somebody else asked the kernel to send you that signal via the kill command, all the kernel does is flips that bit. Done. Signal sent. That doesn't cause you to act on it. Okay? It's like putting a message in your mailbox. It doesn't cause you to read the message. You'll read the message when you choose to read the message. Okay? So when is it that a process acts upon a signal? A process acts upon a signal upon return to user mode. So let's say that a process, ran for a while and got moved to the runnable queue, right? The timer interrupt went off. Boom. The operating system's interrupt handler went off. The operating system, right? We're now in system mode because we went through the vector, right? So now this process is in system mode. The operating system says, okay, your time's up, I want to run a different process, moves that process to the runnable list, and runs some other process. Later on, the interrupt goes off again, the timer interrupt. The operating system scheduler runs and says, okay, process B is done, it's process A's turn to run again. Moves A back, dispatches it back onto the processor. Now, as that system call returns, we transition from system mode, right, executing the timer interrupt handler, back to user mode for the process to resume. So we're transitioning from system mode to user mode. As part of that transition, we walk the pending bit mask from 0 to 1 to 2 to 3 to 4 to 5 in increasing order. If the pending bit is set, we reset the bit to 0 and we execute the handler. Does that make sense? So, upon return from system mode to user mode, we walk our way from signal 0 to signal 31, and for each signal that's pending, we reset it to not pending, and we execute the handler. Once we make our way down to 31, we return, and now we're back to running in user mode again. Let's say you make a system call. Read, write, open, close, fork, whatever. You're now going down into system mode. Okay, so upon return from system mode, at the end of that call, you're again going to check for interrupts. A lot of times when you make system calls, they're going to be blocking. Read is going to require the disk. So instead of getting moved to the runnable list, you'll get moved to a block queue. Eventually you'll be unblocked, you'll be moved to the runnable list. And then when you actually get run, right, you'll be back inside that system call, and now you'll check for interrupts again. Does that make sense? So the two data structures we talked about so far, right, the signal handler array, the pending signal mask. There's a third. Sometimes you just don't want to be interrupted. Have you ever just not wanted to be interrupted? So there's a third bit mask that says blocked. And for each signal, you can set this bit to a 1, which means don't let this signal happen right now. So now what happens is the operating system comes through and flips the pending bit to on. The process eventually returns from user mode to system mode and walks down, we said earlier, the pending list, right? The pending mask. But actually what it does is it executes the handler if the pending bit is on and the blocked bit is not on. Pending and not blocked. If pending and not blocked, set pending to 0 and execute the handler. If pending, otherwise, just keep walking. Now let's say later on you unblock the signal. All that means is you come and flip the block bit off. The next time you return from system mode to user mode, it's going to walk through, it's going to find the pending bit. Okay? And it's going to act upon it. Blocking the signal does not reset the pending bit. Okay? If a signal is blocked and you receive that signal, the pending bit still gets set, you just don't act upon it. Later on, if you unblock the signal, it's still there for you. It still means one or more, though, because let's say that signal comes in 10 times. The bit's set, the bit's set, the bit's set. The lights are on, the lights are on, the lights are on. Lights aren't more on, they're just on. Make sense? Okay. So the three things we can do with a signal, we can, three ways a process can react to a signal. That is to say, if a process receives a signal, what can it do? It can ignore it, it can die, or it can take some other action. Basically with this, I think this is too much detail. Basically what can happen is, a process can block that signal, which means it's not going to act upon it, or it can handle it. Those are really the two options. Right? If you're returning from system mode to user mode, and you're walking through your pending signal mask, right? The two things you're going to do are act upon a signal or not. If you choose to act upon a signal, there are a lot of things you can do. Doing nothing is one of them. That's called ignoring a signal. Do nothing means reset the pending bit, but do nothing. That's called ignoring. Ignoring is different than blocking. Blocking means not now. Ignoring means react by doing nothing. Does that make sense? Blocking is, I can't deal with this right now, come back later, not now, not now, not now, not now, not now. Okay? Ignoring is, don't care, not doing it. Okay? Yes? Oh, sorry. Okay, so, yes?
Could you ignore interrupt?
Yes. Could you ignore, when you say an interrupt, what do you, I guess maybe I need clarification there.
Like this, like the SIG interrupt from the hardware that switches.
Oh, so we're not dealing with interrupts right now. The question was, can we ignore interrupt? Interrupts are hardware things. The interrupt handlers are operating system code and operating system vector. This is a per process software interrupt mechanism. So we can ignore signals, but we can't ignore other stuff. Does that make sense? Yes.
So when you ignore it, does it turn that bit off, like blocking?
Yes, sig ignore is an action where that bit gets reset.
Okay.
That is actually what's called a disposition. Okay, ignoring is one disposition for a signal. Okay, blocking is not a disposition, it just means we're not dealing with it. Okay, it's still there to be dealt with, we're just not dealing with it right now. Okay, so one thing we can do is we can ignore a signal. Another thing we can do is act upon that signal. Acting upon that signal can be doing anything on Earth, basically. Okay, one common reaction is to die. Right? If somebody hits Control-C, it sends your process a SIG, SIG interrupt, and your process dies. And basically, there are two different ways of dying. One is dying with a core dump, and one is dying without. Okay? But you can have a handler that does something else. So I'll tell you a story. When I was a sophomore, I took a class called Computer Science 360. It was directly out of the 1970s. And by the way, I am not that old, just in case you're curious. It was called File Structures and Peripheral Design. And it dealt with everything from the physical design of storage systems to the bottom half of a database. B trees, external hash tables, things like that. And our final project was basically to write the bottom half of a database. Indexes and whatnot, basically B tree based. And the instructor didn't have a test set or anything like that. You wrote your project, and then you went to his office, and then he tested it. And then he gave you a grade. Every project was tested differently. But the rule was that if your project crashed during the demo, you failed the class. Okay? Yet grading was completely non-standardized. And so I had this fear that, you guys know me, I'm a disagreeable person. No one likes me. So I had this fear that I was going to go and I was going to, go for this demo, and that he was going to give me the extra special tests. That I was going to stand there until he broke my database, causing it to crash, and then I'd flunk the class. And somebody else would walk in with a half-working database, and he'd be nice to them and never run any hard tests. And so I got myself really upset this was going to happen. And this just was going to be totally unfair. And so I decided the only thing that I could do to solve this problem was to build an uncrashable database. It's an easy thing to do, right? As it turns out, it is. So what I did is I used signal handlers to catch any reason the database would crash. Segment violation, bus error, divide by zero, floating point exception, and so on. And you'll learn how to do this today. So I added my own handlers to these things. And so if any of these evil things happened, it execed a new copy of itself. Okay? So if it was trying to do whatever it was doing, and it seg-faulted, it would exec a new copy of itself, replacing the bad process image with the new process image. And the way databases work, they have these logs, where they write, it's called a write-ahead log. They write what they're going to do before they do it, then they do it, and then they close the transaction. And so it execed a new copy of itself, and the new copy always read the log first. And if something was undone, it tried to do it again. Does that make sense? So some test case was fed to this thing. It choked on the test case, so I execed a new copy of the program, which resolved the segment violation or bus error, whatever it was. Upon bootstrap, right, upon startup, the program read the log, backwards actually, found that this transaction was incomplete, and tried it again. The theory here is that the most likely reason the database would crash is that one of the in-memory caches of the on-disk data structures was bad. I had some just memory error, right? With luck, I didn't actually corrupt my database. So it tried it again. With luck, it succeeded. If it didn't, what did it do? Of course, it execed itself again. This time it went back to the log and saw the same thing was tried twice. Oops. So the next thing it did was assume that there was some edge case in the shape of the tree that was causing this problem, and gave the tree just a massive twist. Pretty randomly, actually. It went like 2 steps down the database and then twisted the B tree, hoping to resolve whatever edge special case it was. And then tried it again. Let's say it failed again. This is the 3rd time. 3 strikes and you're out, right? So what do you think the database tried the 3rd time? I could skip it, but that would have less of a sense of humor than I had. It took the user's, bizarro query and introduced a syntax error and spit it out and blamed the user. Introduced an extra, it added or removed a parenthesis or squiggly. The next time it introduced a new error. It had a few rules for introducing errors. One was like add a squiggly, one was remove a squiggly, one was delete a letter from a command, one was to reverse 2 letters in the command. It did not crash.
Did you use extra hard test and did you have to use the syntax error?
I don't believe it ever, it never got to the point of introducing an error in the query. That much I know. The rest I actually don't know because I didn't go back and look at the logs. And so, to answer whoever's question that is, can we catch these things? The answer is yes. And there are good reasons to do that, like passing your computer science 360 demo, or solving any other robust software problem that might parallel that. Okay. Processes, there's this abstraction called process groups. If you think about the command line and you type ls, pipe cat, pipe fold, pipe more, right? Pipeline a bunch of commands together. This group of commands that are pipelined together forms a process group. What's special about a process group is the whole group only has one input and one output, right? The first command has an input, the last command has an output. The rest are daisy-chained, output to input, output to input. That's the reason we have process groups. So when your shell forks off a new process, a real shell forks off a new process group for every process group. So if you type ls, it's put into a new group. If you type ls, pipe cat, pipe fold, pipe more, each of those newly forked processes is put into the same new group. Does that make sense? Okay. The first process put into a new group is called the process group leader. There is nothing special about that. It sounds really great. It's like cafeteria monitor. Okay? It doesn't sound so good when you realize what it is. The only thing special about a process group leader is that the process ID of the process group leader becomes the group ID of the new group. The first process put into a group lends its name to the name of the group. That is all. The group can outlive the leader. Okay? Yes?
Background processes not have children?
Background processes can certainly have children.
Okay. I'm just checking this.
Oh, in this case, they don't happen to, but they can. Okay? So the neat thing about process groups is that if you think about it, there is this thing called the terminal, right? And like back in the day, it was a physical device, right? We don't have, like, when you talk about a terminal these days, you're talking about like your Xterm or something, right? You're not talking about a real terminal, okay? You're talking about an abstraction that involves a text input device and a text output device. So basically, every so-called session is associated with a controlling terminal, the abstraction of a keyboard and screen. All right? And that is associated with your so-called session. The definition of a session is that it has a controlling terminal. The controlling terminal is just virtualized, right? Your same real keyboard and screen serve all your Xterms. Okay? Now, within this session, we can have one process that is foreground, one process group that is foreground with respect to the terminal. This is different than with respect to the user. What this means is that the keystrokes go to that process group, and the output of that process group goes to the terminal. Does that make sense? So if I have five different process groups, only one can be interacting with the keyboard and screen at a time. Does that make sense? Otherwise, like you type hello, and which process gets it? Okay? If you type Control-C or Control-Z, right? That gets sent to each process in the current process group. The current foreground process group. Does that make sense? What happens if a background process or process group tries to read from the terminal? The terminal says, you're not allowed right now. No. Zap! And it sends it a sig TT in, sig terminal in. The default result of which is suspend. What happens if a background process tries to write to the controlling terminal? Zap! Sig T out, sig terminal output. In other words, you're not allowed to write right now. The default result of which is suspend. Now you can tell the terminal, dear terminal, please allow background jobs to be able to write. So-called terminal attributes. And if you do that, okay, if you set your terminal attributes and tell it that, then background processes will be able to write. Yes?
So like, when we're working on our 213 homework really late at night, and it says the system's going to reboot in 260 minutes, and just like writes into the middle of your Emacs file or something. Mm-hmm. That's where you've set it so a background process can write to the terminal?
Well, that's a little different. The question is when the system wants to write to your terminal and does, do you have any control of that? And the answer is not really, because the system has privilege to do that. It's going to ignore your terminal attributes. But if you run a process in the background, sort of the normal way is that if that process tries to print a message that says done, it'll get suspended.
So I guess my question was, that's the system, not some process that has had its
right. I mean, the system things are going to ignore your attributes, and they have privilege to do that. Right? But the more common case is you run some long-term process. Sort of the nominal default is when this process is done, it'll try to print something like done to the console. But now it gets suspended because it can't, doesn't have the privilege, it's background. That sucks. So in that case, you might change your terminal attributes, use like STTY, or whatever, right? Set your terminal attributes and say background processes are allowed to write. And now, when that process finally ends, you get an annoying message across your screen, but at least you know that it's done. It was worth it. Does that make sense? You can't really allow background processes to read because that turns into a mess. Which one gets the character? Yes?
So when we, let's say we're working on Cache Lab and we're testing one trace. and it can print, if say we have it just riddled with printf statements so that we can watch it. But then we run tests on everything, and it doesn't print out anything we've told it to print. Is it running everything else as a background process and saying, no, you can't print, we're just testing? Like, how is that?
I would have to see what your make script looks like to know why it's not printing.
Well, no, like the test files, the testing stuff you guys give us in
Oh, okay, so I would have to look at the details to know why you're not seeing that output, but it could be that it's running in the background, that it's not able to write. I would have to look to see.
Okay.
I'm just not familiar enough with that piece of the machinery to give you a good answer.
Okay.
Drop by for office hours, I'll take a look.
All right.
Okay. A process can find out its process group by using get process group. Okay. It can change the process group by using set pgid. Notice this is grp and this is gid. All right. The kill command at the command line can be used to send signals. Here we're sending a signal 9, which is a kill, to, notice this negative. This looks like process ID negative 24817, but that's obviously not what it is. A negative process ID indicates a process group. So now we're sending a kill negative 9 to the process group 24817. Now, 9 looks like a signal, but it's not. 9 is sometimes called a sig kill, but it's actually not a signal. It's a request to the operating system to delete a process. So this is sort of a bad example, because we're not actually sending a signal in this case. We're saying, dear operating system, please delete process. Yes?
So the set group ID function,
Yeah.
when a process calls that, is that changing which group it is in, or changing the ID of the entire group that it's a member of?
As I remember it, if you specify a 0, it's you. If you don't, it's specifying another process. And you can only change the group of a process that's your child.
Okay.
But check the man page for the details. Does that answer your question?
Yeah.
Okay. Okay. So Control C, right? When you type Control C, right, the terminal sees Control C and recognizes that it's special. Its reaction is to send a sig int to every process in the foreground process group. If you type Control Z, the terminal recognizes that as special, and it sends a sig T stop, terminal stop, okay, which will cause the process to be suspended to every process in the foreground process group. If I look at a process list, S stands for sleeping, R stands for running, and T stands for stopped on a terminal control signal. T in, T out, T stop. Okay? A lot of times you don't actually see a process show up as running, because the moment you happen to look, there's not one actually running right now. They're all waiting for I/O, waiting for something else, which is what the sleep state is. If instead of doing this at the command line, I want to do this in a program, I use the kill function. Kill, the process ID I want to send it to, and the signal I want to send. SIGINT being the same thing as what's sent with the Control C. Again, if that process ID is negative, it represents a process group number instead of an individual process number. In that case, it gets sent to every process currently in that group. We talked about receiving signals. Right? Upon return from system mode to user mode, I'm going to walk that mask from signal 0 to signal 1 to signal 2 to signal 3, and I'm going to execute the signal handler if the pending bit is set and the blocked bit is not set. Okay? Most programs we write, we don't want any special signal handlers, right? We don't want to think about signals. We just want to do what we're trying to get done in a normal way. And so each and every signal has a default disposition. What happens to it if we do nothing? Okay? If we want, however, we can replace the signal's disposition. Rah! We show here this function called signal. This is like right out of the 1980s. Okay? We're going to show this in the rest of this class because that's how the book is written. But the proper function, I want everybody to look it up, is called SIGAction. SIGAction is a much better way of handling signals. Okay? So when you get a chance, do a man on SIGAction and see the difference. This is the simplest way, but sig action is much more flexible and actually more correct in certain situations. But the signal function call is actually really easy. Okay? You write some function that you want to execute when the signal runs. You call signal. You give it the signal number, right? You shouldn't do that with a real number. You should do that with one of the pound defines, like sigint or sigcont or whatever. And then you give it the name of your function, which serves as a pointer to that function. That's it. When whatever signal you specify here occurs, that will run. You've now changed the default disposition. If you want the default disposition back later on, over here you can specify sig_DFL, all capitals. And that will reinstall the default handler. If you want to ignore it, you can install sig_IGN, sig_ignore. And that'll install the do nothing handler, basically. Okay, sig_IGN, sig_DFL. So here we have a handler. Okay. Because some handlers take multiple signals, for example, the disposition that causes us to die and dump core might be appropriate for many signals. The signal handler function takes the signal that's actually called, which will allow it to do things slightly differently depending. Okay. And so we have our signal handler. We come over here and install our handler, signal, sigint, and here's what I mean. Don't use the actual number. Use the pound define for it that's in the header file. Okay? Which header file? Signal.h. And then we install our handler. Our handler is called int handler. There we go, int handler. Now when the process is sent to sigint, this handler will run. Yes?
Where are we getting n from?
Which n are you looking at?
The I less than n, or like PID of n.
Oh, I mean, this is only a code segment that's coming. This is only a.
It's some global or macro.
It's somewhere else. Yeah, this is just an excerpt.
All right, thank you.
You're welcome. Okay. And now you can see that this thing prints process 1, 2, whatever the process ID happens to be, receive signal, whatever signal happens to be. And now you can see that. Process, there are the process IDs, receive signal, signal 2. Okay. The nasty thing about signal handlers is that they're asynchronous, right? A signal can occur at any point in your program. It can occur at any line of high-level code. But even worse, as you guys know, high-level code, one line of high-level code, often translates to a long chunk of assembly code, right? So that signal can be injected anywhere in that assembly code. It's like having a function call pop in, right? Suddenly, in between two lines of your assembly, there's a call to some function that you didn't know about, and there's some action and a return from that function you didn't know about. So you've got to be really careful. You don't want to be in situations where, for example, things in your signal handler, okay, change static state. Let's say you're using, I don't know, like a string toke or something like that, that has a static local variable. And now you access that from your signal handler. Now your code's messed up, right? Because it suddenly had this state that was changed that you weren't expecting. So you've got to be really careful about that. It's an example of concurrency. Sigchild is an important signal, right? If our child dies, sigchild lets us know about that. This is important because we need to reap it. When people start to go to write their shell for this class, there's a temptation basically to fork, exec, wait, and then loop back and do it again. This works until they introduce background processes. And then what happens is they can't wait there. So then the next thing people try to do is put an if statement around that wait. If not background, wait. But then the problem is you're building up a whole bunch of zombie background processes. So then people go and they add a signal handler. And they put a wait into that signal handler. The theory being when the background processes die, they'll send a sigchild. The sigchild handler will run. And then the wait inside the sigchild handler will solve the problem. At this point, most people are 95% of the way to the solution, but 110% confused. Because what happens is a whole bunch of really weird things start to occur. For example, when the foreground process dies, Does it send a sig child? Yes. The foreground process dies, the kernel sends a sig child. The signal handler handles that signal. You return, and now you're stuck in the wait, which will keep waiting because the process has already been reaped. Something like that will happen to you. Okay? So one thing you want to keep in mind when writing your shell is you should only call wait in one place, and only one place. And that one place should be the signal handler. Otherwise, you're going to get into trouble. Okay? The second thing that happens to folks is that by the time the signal handler runs, there could actually be multiple dead children, multiple zombies. Okay? Because you could have launched 5 background processes, and they could start to die. But you're still happily running in user mode. And it's not until you drop into system mode and return from system mode that you check for sigchild. So now you check for sigchild, you call wait once, and you reap 1 of 5 zombies. Oops. You need to reap all of the zombies. Well, how do you do that? Well, you put that in a while loop, right? But then the next problem people have is when it runs out of zombies, the wait freezes. Right? Because wait waits until it does something. So what you need to do is you need to add a flag to that wait PID called wNoHang, which basically says reap a child if there's a 1 available, otherwise don't. Return immediately. And then you'll find that you can check the return value from wait to figure out what's going on. Wait will return a PID of a child that it reaps if it reaps a child. So if it returns if it returns a positive number, that tells you it reaped a child. If it returns a 0, that says no children are presently ripe. And if it returns a -1, that says sorry, nothing matching. Nothing in that group if you were waiting for a group. That process is not around if you were waiting for a process. Right? Nothing at all if you were waiting for any of your children. So you have to care about that. Okay? You also get into some weird race cases when you go to write your shell. For example, what happens if you fork off a process and it runs and finishes and sigchilds before you do things like add it to your jobs list? Then the sigchild looks to remove it from the jobs list but can't, and probably just ignores it. Then you go back to running the parent, and it adds it to the jobs list. Now your jobs list has a ghost. So you actually need to do things like block signals before you call the fork until after you add it to the jobs list. That way you're sure it's in the jobs list before you unblock it. And now allow yourself to handle that. And so there's a lot that goes on with this concurrency. So think your way through it. Okay. Here's the no-hang example. Okay. While my PID returned by wait is greater than 0, well, I've actually reaped a process. Loop back and reap some more. Okay. Use wNoHang so that if I'm out of children, this thing will return something that's negative or 0, and get me out of the while loop. Okay. If you receive a signal while in a blocking system call, the blocking system call returns immediately. So if you are in a read or a write, something like that, that's a blocking system call, where it could be waiting for disk or waiting for the terminal or waiting for the network, or wait, or something like wait PID or wait, that's blocking waiting for a process, and you receive a signal, that system call terminates immediately. Okay? And sets the global error number to EINTR, error interrupted. Why? You don't want to be in a blocked system call, okay, and sitting there getting hit with signals that say die. And meanwhile, you're staying blocked. SIGINT, 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 SIGINT. Okay? So that's why they have that rule. But that's a pain in the neck for most of us. Okay? Because like we don't want to loop around every one of our blocking system calls. I mean, every printf has a write underneath it. So this is one of the reasons I suggested that you use a sig action instead of signal to install your signal handlers. Because if you use sig action, you can specify a flag called SA_restart. Signal action underscore restart. SA_restart. And what this says, you install your handler with the SA_restart flag. And what that says is automatically restart any blocking system call interrupted by the signal handler. It causes the system state to be checkpointed, the handler to be run, and then to pick up where it was checkpointed. Okay, so it restarts blocked system calls. Much nicer than having to loop around all of them. Okay. This is not, I don't believe this statement is true. I think in order for a read to be restarted, you need to specify SA_restart in the signal action. You can check the man page on that, but I don't believe there's anything magical about read. Okay. Here's a version of printf that your textbook uses. That's a signal say that's a reentrant safe printf. Nothing magical about this. It reacts. You know, the thing that's magical, I guess, about this particular example, right, is that it signals itself. Okay, it uses alarm to send a signal to itself. Alarm basically says, send me a sig alarm in 1 second. So you can ask for an interruption at some time in the future. When it comes to looking at library functions, not all library functions are interruptible. Only those that are listed as async signal safe are safe. 117 functions apparently in the POSIX spec are safe. Write is on the list, but printf is not. So, you know, Dave, who's one of the authors of the textbook, wrote this safe printf that uses VSN printf, which is a safe version of the printf, to emulate printf. And so he wrote a signal safe printf called safe printf. Non-local jumps. This is sort of a random topic, but one we'd like to talk about. Okay? Where you are in execution, right, is captured by the state of your stack and the registers, right? So what we can do is we can use a call called setJump to save our registers into a buffer. Okay? And then we can make, for example, a whole bunch more function calls. And then we can use a function call called longjump, giving it that buffer, and that will restore our registers, including our stack pointer and base pointer, which has the effect of bringing us back up the stack to where we saved our state. Okay? This is sort of used to implement exceptions, to checkpoint places on the stack so that if you're trying to, in effect, throw an exception, you can jump back to that point. Does that make sense? So basically, when setJump is called, it returns 0 indicating success. When longjump is called, you specify the return value here. And then when you return from setJump, as a result of the longjump, it returns that value. In other words, the first time I call setJump to save my state is saved within the setJump. I then return 0. I successfully saved my state. Later on, when I longjump, I'm restoring myself to where I was inside the setJump. So setJump is going to return. Just like fork returns in 2 children, right? setJump is now returning again. I can set the value when I do my longjump that will be my return from the second return from the setJump. You should not return 0 or you won't be able to tell the difference. Right? You want to have setJump return 0 the first time and 1 if you've jumped back to it. That way you know you've jumped back. Set jump and long jump only works if the stack frame is still valid. So I can long jump back if I've gone down, but I can't long jump back if I've returned up past that point. Does that make sense? You can only jump up to a valid stack frame. If the frame you saved is not above you in the stack, you can't jump to it. You can only jump to it if it's in your current call chain. You can't jump to it if you've returned from it and you're done with it. Does that make sense? Don't long jump back to an invalid stack frame. Yes?
How would you do that? Like,
how would you do that?
yeah, just like what would cause that?
You would set jump at some point and save the thing. You would then return from a whole bunch of functions, pass the original call, encounter some error, and say, shit, I'd better bail out. Long jump. But you've already passed your bailout point. So that stack frame that you're bailing out to is invalid. It's like when you throw an exception in Python, right? Or Java or something. The exception gets passed up the stack. It can't get passed back down the stack. Does that make sense? Same way here. Does that answer your question? You sure? Okay. All right. So here's an example where we call set jump in main and we save our status. In the event of some error, we long jump back to there. The first time we call set jump, it returns a 0, so we print out first time through. When we encounter the error and we long jump there, it's no longer 0, so we print out back in main due to an error. Yes? No? Red shirt? Okay. Limitations, like I said, you can only jump into a valid stack frame. Okay. So here's a program that restarts itself when a SIGINT occurs. So we use something called sig set jump, a signal safe set jump, and we save our position. Then we print out starting. When the user hits Control-C, we land in the handler, right, that we installed. And there we long jump, this time with a return of 1, back to here. Since the return is 1, it's not 0, we print out restarting. Okay. And now we can see every time we hit that, we see, restarting. Okay. Inside processing, boom, 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 boom. Eventually we hit Control-C, then we see restarting. Then we're back here processing, processing, processing. Someone hits Control-C, we're in the handler, we jump back, restarting. Yes?
If we keep handling SIGINT, how do we ever kill it?
So if you keep handling SIGINT, like my undefeatable, right, undefeatable database, you have to send it some different signal. Sig kill can't be blocked. Like I said, it's not really a signal, it's really a request to the operating system to delete the process. So SIGINT can be blocked, but sig kill can't. So summary, signals provide, right, sort of software interrupts. They provide process level exception handling. They can be generated from user programs. They can be generated from outside user programs. They take defined actions which are defined within signal handlers. One problem with them is they're very slow, more than 10,000 clock cycles to handle an interrupt. They're not made to be done very often. And they don't have queues, right? The only thing you can tell is that one or more of that signal has been sent, not how many. Non-local jumps are a lot of fun, but of course they work within the constraints of the stack discipline. You can't jump to a stack frame that doesn't exist. That isn't valid. Any questions? All right, have a great day, everybody.